All right. Can I press the go live button?
Yeah, I'm just pulling up patrons and stuff.
So did you watch the launch of SpaceX?
That SN10.
Yeah.
I loved that so much. I was watching the NASA spaceflight stream and hanging out in Discord with a bunch of our CosmoQuest people. I also had the SpaceX stream up, but it ended.
Mm-hmm.
So we're sitting
Apparently
there
there was
yammering.
more to the story.
Right. And so like going into this, we'd all had our predictions. And my personal prediction was it would land at the correct velocity, but would fall over at some point. And so we're all watching it because it's leaning ever so slightly to see which of us have the correct predictions.
Yeah.
And all of the sudden,
boom.
It was like it decided it was going to try for that second launch.
Yeah, second launch.
Yeah.
Flew twice.
Oh, man. It was just...
It was amazing, though. It was amazing to see the
was.
3 engines come on, the thing do the flip, land. But even when it landed, you could tell it was a really hard hit. It came in hard. And I watched that and just went, ooh, that's not good.
And I didn't realize how tiny its little legs were.
Well, compared to a giant rocket, I'm sure they're, as big as a house, but yeah.
Well, even proportionally compared to the ones that Falcon 9 has. So itty bitty little legs.
Oh, maybe. I don't know. Yeah, and I don't know if you saw, Scott Manley did a great breakdown where he watched the rocket come down, and in the frames just before it landed, you could see a bunch of the legs locked into place, but like 3 of them were swinging and they weren't actually locking down into place. And so
and that's part of the landing sideways. And what was amazing is some of the stills that people have caught from the videos, and I accidentally caught one myself, where you can see the seams in the bottom of the rocket where flames are coming out.
And also you could see the top crumpling as the bottom is accelerating upward.
That was surreal.
That was amazing. Yeah.
Because I first saw the crumples in one of the images that came out from Lab Pedro. And then I went back and looked at the screenshots that I had taken right after landing. Yes, thank you.
Yeah.
I didn't have those crumples. And then I realized, the top hadn't started moving yet. And yeah.
Amazing.
Awesome.
So, we're not there yet. At least it still fulfilled the rule that starships have to explode. That's what they do. So even though it did stick the landing, it also exploded, which is to sort of make sure that it didn't miss out on a noble lineage.
But every time they fail in a new way, which is exactly what you want from iterative design. I do iterative design as a programmer.
Yeah, good point. Yeah.
I just don't need to worry about things generally exploding. I have had one computer catch itself on fire, but that wasn't due to my code.
Yes, I was wondering. It wasn't your doing.
No.
Yeah. Yeah, no, for sure. My voice is a little gone today.
Go get something to drink.
I got some water, so I should be okay.
Okay.
Anyway, you do all the talking for this. I just get to kick back and listen. All right.
A picture of you closer to where the video. Hi, dog. That's not gonna work. Okay. There we go. She backed up. We'll see if she stays.
All right. I'm ready with my intro and all that.
Oh, I have to open the audio recording software because that is what we do, isn't it?
Yeah. Among other things.
Okay. This is 598.
Yes. Oh, sorry. Yes. That wasn't a rhetorical question. Yes. Scott Bragdon says, the astronauts are getting ready to fly. They must be getting nervous. Yeah.
Yeah. Which set of astronauts is it this time? There's so many sets I can't keep track anymore.
Oh, no, on the Starship.
Oh, yeah.
Yeah.
That. Okay. Hold on. I'm juggling the dog. There we go. Getting the monitor out of frame. All right. I think we have reached a stable configuration.
Have you?
No, because the other dog just climbed up. Are you going to lie down?
Each time you think that the solution is more dogs, but it's not. It's not. These dogs are really underfoot all the time, but if we get one more dog, that'll perfectly balance it out.
They're supposed to play with each other.
Yeah.
Unfortunately, I am the favorite dog toy and favorite dog
That's
bed.
how it works. I believe that's how it works with children too. Like, oh, we need to have like a little brother or sister for our kid, and then, it's the equivalent of 5 children.
Yeah. All right. Okay. I'm ready to press record. Are you ready to?
I'm ready.
Okay, I am pressing record. Hello, Rich. Hello, Allie.
Hello. Okay, here we go. Astronomy Cast, episode 598. How you could overturn cosmology. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. How are you doing, Fraser?
Did I mention that I'm over the pandemic last time? I'm still over.
Yeah.
I'm
Yeah,
done.
my husband had to go get COVID tested today, so good times.
Yeah.
Oh.
Yeah, I discovered at my kid's school. It's rampaging on the island. And yet, there's like all of this amazing vaccine news. And then there's also all this sort of scary variant news.
Yeah.
So it's just like it's no longer the action adventure. Now it's just reality surviving. Yeah. It's what it would be like to move to Mars. In the beginning, you'd be like, woohoo, I'm on Mars. This is an adventure. And then after a while, you'd be like, oh, this is horrible.
Yeah, mistakes.
Mistake. Yeah, I'm sad and alone and I want to see an ocean.
Yeah, one of the interesting side effects I'm dealing with is because my husband was potentially exposed, we're trying to quarantine, which means I can't really lock the dog somewhere else. So I am currently swimming in dogs.
Yeah.
And I keep brought toys.
Squeaky toys.
This is the most recent toy I have been brought. And I'm dumping them behind my chair so she can't squeak them anymore. So if you see the sudden movement of an object being dropped behind me, this is because I've been quarantined with 2 dogs and they have ideas.
I think as a podcaster, I think it's perfectly within your rights to extract the squeaky toys from the squeaky part from the squeaky toys.
Yeah, I'm just also lazy. So
Right. Okay. Well,
dumping them behind the chair works.
Sure. All right. You've probably heard of dark matter and dark energy, but maybe you don't fully understand what they are. Or maybe the idea itself just rubs you the wrong way and you'd like to know why scientists think they can just make stuff up like this. So you'd like to overturn cosmology. Well, here's all you need to do. And we'll talk about it in a second, but first let's have a break. And we're back. We've probably mentioned this in past podcasts. This is a constant thorn in our side that something about dark matter, just don't like it, man. And I think, I feel like last week we got to the heart of it, which was that the neutrino is essentially dark matter, just hot dark matter as opposed to cold dark matter. And nobody has a problem with it. Except the name.
Yeah.
It's the name.
Yeah. And this week in particular, we've seen in the journals a number of papers popping up trying to find ways to deal with dark matter, dark energy. And I know my inbox, I suspect your inbox, we get this steady stream of emails from people asking us to review their theories.
Yes.
And they always ask us to keep everything in confidence, and they mail it all to us before we agree to that, which always confuses me.
Yeah. Yeah, that's not how it works. That's not how non-disclosure works. I mean, for starters, I will never agree to that. Like, ever. Like, if you want to send me I've mentioned this in the past, that, you know, at Universe Today, we don't agree to embargoes. So, but yeah, if you want to send us information, then you've already kind of broken it. I think that's a really valid point. But yeah, absolutely. I get these one a day, maybe. And I mean, and it's funny for me, like, sending me your theory of cosmology is worthless. Like, what am I going to do? I'm a journalist. I'm an
observational astronomer. I do not want to go through your theories.
Right.
That would require me reviewing far more literature.
Yeah.
I want to deal with photons and computers.
And you're a specialist.
Yeah.
Yeah. So it is funny. And I mean, I think we know why, because
we're here.
We're here, yeah. And no, but they feel like they can't get respect from the scientific community, and so they're going to try to come in on the edges, try to get some respect through the journalists, the publicity side. I don't know. Anyway, yes. We get them. Yes. Can confirm.
Yes. And the combination of getting these emails and then seeing stuff that goes through peer review that you got to wonder who reviewed it just got me to thinking, we really need to go over, here are the things, all of the different things you who are sending us these things or trying to get them published need to address in the first few paragraphs of whatever you put together to let us know it's worth reading further.
All right. So then let's pick what, I mean, do you want to just talk about, like, just overall general cosmological ideas? Do you want to just talk about specifically the evidence, sort of all of the evidence that stands for the individual theories? How do you want to tackle this?
Let's take a look at what are the things you have to meet for dark matter and what are the things you have to meet for dark energy.
Sure. Dark matter. I choose dark matter.
Okay, so dark matter. It was first discovered because galaxies don't rotate the way you would expect them to based on luminous matter. A individual object orbiting around our system is going to have an orbital velocity that is directly related to how much material is inside of that orbit.
Mm-hmm.
And you would expect things to go slower and slower the further out you get, because the amount of stuff inside is dropping off instead of increasing. But when you look at it, it turns out that velocity actually flattens out instead of dropping off.
Right. And so just to give sort of a finer point on this, right? Like Mercury orbits at something like 45 kilometers a second, while the Earth orbits at 30 kilometers a second. And Neptune orbits at 5 kilometers a second. And so the farther away you go from the sun, the slower your orbital velocity is. Because, as you say, you're orbiting around this center of gravity. And so you would expect the stars orbiting around the center of the galaxy are going to go super fast. The ones in the middle are going to go middle speed. And the ones way out at the edges are going to go slow. This is what you would expect to find that you would see if a galaxy was a big solar system.
And it's not. So we know that you do have to take into account the fact that, like, there's a whole lot of stuff in the center of the galaxy. There's bulky arms filled with gas and dust and star formation. You have to account for all of this. But as you get far enough out, you run out of stuff that you can see other than the occasional cloud of hydrogen gas. And so you'd expect, looking at those clouds of hydrogen gas, that their orbits would slow down in relation to the lack of extra stuff getting thrown into the galaxy that we can see. And they don't, which means there's a bunch of stuff we can't see that's out there.
And so pretty much anywhere you measure the velocity, the orbital velocity of a star going around the center of the Milky Way, it's the same. It's whatever, it's 250 kilometers a second, I think. So if you're close in to the center of the galaxy, it's that speed. If you're way out near the outer edges, it's the same speed.
And
And so, like, that alone should tell you that something weird is going on.
And up until the 2000s, all we knew was there was an effect that was either we didn't fully understand gravity, or there's a whole bunch of stuff we can't see, and we didn't know which,
Right.
that was affecting the rotation rate of galaxies. And we also saw this in terms of the orbital velocities of galaxies in clusters. As we scaled up where we were looking, these massive systems, but not our solar system, massive systems like our Milky Way, like our cluster, like the Virgo supercluster, all of these bigger systems had this extra effect. And so for a while, you could successfully more or less debate, is there this stuff we call dark matter, or do we need to modify gravity? Is there a modified Newtonian dynamics out there?
We just don't understand gravity.
Right. So both these things were possible. But then there were the amazing observations of the Bullet cluster, which people looking at this system, which is two merging galaxy clusters, becoming a bigger galaxy cluster. You could see where the galaxies are in the merging system. And you could also look between the galaxies in this cluster at the stuff behind it and see how their light was distorted by the gravity of everything in these clusters, including that dark matter. And because we can see that whatever this stuff is that's causing galaxies and stars to orbit faster is also having an effect on light, we knew that it is something that has a gravitational pull instead of an extra term to gravity, because an extra term to gravity isn't going to affect the stuff behind the mass. So suddenly we had this, okay, so it's not modified Newtonian dynamics. And since then, we've been trying to figure out, by looking at the dynamics of how the dark matter appears to be clumped based on its gravitational effects.
All right, well, let's talk about how astronomers actually observe and map out dark matter in a second, but first let's have a break. And we're back. All right, so since that observation of the Bullet cluster was made, astronomers have gotten better and better at seeing dark matter. How do they do this?
It's all about assuming that galaxies on average are circles. That if you look at enough galaxies, some are going to be edge-on, some are going to be flat, some are going to be mushy messes. But on average, all of these different galaxies, it can be oriented in every possible way. Because they should be randomly oriented on the sky, they should have an average shape that's a circle. So if you look at a patch of sky that can contain thousands of galaxies, if you look hard enough, you average together all those shapes. And if you don't get a circle, that means there is something out there casually distorting the light like a funhouse mirror using gravity. And this is exactly what astronomers do. We look at chunks of galaxies in this volume of space, chunks of galaxies in a further back volume of space. And we look at all of the distortions and how they add up layer by layer through the volumes. And this allows us to see where the dark matter is by how it warps what we see behind it. And there's projects out there like Cosmos that have actually been able to do three-dimensional maps of volumes of space showing the clumped up, lumpy mass that is dark matter in our universe.
And so just for anyone working on the theory, keeping count, you have to explain the rotation of galaxies, how they hold themselves together, and how the stars orbit at constant speeds, no matter how far away they are from the galactic core. You have to explain how galaxy clusters can collide and separate themselves out into hot gas and galaxies themselves. You have to explain the micro lensing that's done, or the gravitational lensing that's done across the universe to see all of these distortions of from some sort of thing with gravity, and many more. Like we're just scratching the surface. There are now, I would say, probably like 10 separate lines of evidence out there now that show that dark matter is a thing.
And it also is required to explain how rapidly galaxies and supermassive black holes were able to form at the beginning of the universe. This is something we went into last week, where if we don't have cold dark matter as the bulk of the stuff our universe is made of, then you can't get the first supermassive black holes as fast as they appear to have formed in the universe. You don't have enough stuff to draw in all the luminous matter to form stars and galaxies as early as we're seeing it in the universe.
Now, you say it has to be cold dark matter. And, why is the cold part important?
It all comes down to collisions. If you have material that is hot, it's moving a whole lot faster. And so particles are less able to collapse down and form clumps. A good way to think of this is if you've ever gone ice skating or roller skating with a bunch of friends. If you come up to a friend and your velocities are close to the same and you're not going too fast, it's super easy to grab onto each other and to continue skating together. But if you're whipping around at high velocities, even if you're both going at similar high velocities, coming together without bouncing off and colliding wildly or just missing each other completely is much more difficult.
I like the idea of, like, if you want to make ice cubes, you either start with cold water that's in the fridge, or you start with steam coming out of your kettle, right? One's tough. One's harder to make ice cubes with. Until you cool it down. And so this is why neutrinos, and we talked about this last week, neutrinos are a thing that has been discovered that is essentially invisible, could pass through a light year of lead 50% of the time, can go right through a light year of lead, not stop, not interact. You have countless, hundreds of millions of them going through your body right now, thanks to the sun. You don't even feel it. And so the difference is those are hot.
Yes.
And so dark matter is going to be a particle that's kind of like a neutrino, except it's not hot. It's going to be cold. It's going to be slow moving. So you, instead of having
to clump up nicely.
Right. Instead of having neutrinos passing through your body at close to the speed of light, you've got dark matter particles moving through your body slowly. And that's what cold means.
Yes.
Okay. I think that sort of, I'm sort of thinking about the time, and that gives us a good list of, like, the top things to try to describe. These observations are in many cases rock solid. So if you think those observations, then that's where you start. Is you've got to overturn those observations. But if you trust in those observations, then your theory has to explain those things. Plus, like I said, another 7+ lines of evidence.
Those are just the big ones.
Yeah. Let's go on and talk about dark energy in a second. But first, let's have another break. And we're back. All right, dark energy. Badly named, I think. I mean, both are badly named.
They're both. So one of the things that is very true is an astronomer does not need to understand a thing to name a thing. Which
Right.
means that if there is this nebulous, unknown quantity causing an effect, we are completely down with naming it without knowing what it is or anything else about it other than the effect it is causing.
Well, I think you had one of the greatest analogies, and I've used this many times since you presented it, which is that your car is making a funny banging sound as you drive. You don't know what it is. It could be the wheel, it could be the hub, could be the axle, could be the transmission, could be the steering wheel, could be all kinds of things. Could be a rock in the tire. It could be something. You don't know what it is. You know it's there. And anybody who comes and sits in your car for 5 minutes goes, yes, I agree with you. There is a banging sound going on in this car. Let's call this dark mystery noise. Agreed. And then now let's try to figure out what's causing it. And so I think we're at the dark mystery noise point in our story.
And if you have a rock inside your tire,
Well, stuck
kudos.
in the tire. Well, stuck in the tire, you know.
Okay.
Yeah,
Okay.
Yeah. So let's talk about the observational evidence for dark energy.
So back in 1998, a couple different teams of supernova observers realized that as they looked at type 1a supernovae, which should all be more or less the same brightness, there's exceptions, don't add us. They should be more or less the same brightness. When you look at them at a variety of different distances, the rate at which the universe is expanding at all those different distances is such that our universe is accelerating. Things were moving slower in the past and they're moving faster now. And what was expected was either the velocity would be constant over time, the rate of expansion would be constant over time, or it would be slowing down.
Right, slowing down is what you would expect. Yes.
I'm good with constant, but yeah, slowing down makes the most sense.
Constant's a little weird.
It's a little weird,
yeah,
but I was good with it.
Okay.
I'm not okay with this acceleration that we
yeah.
actually have.
And neither were the astronomers.
I am an astronomer.
No. I mean, the ones who discovered it. The ones who discovered
true.
dark energy were not looking for dark energy. It was it was a surprise.
And they got a Nobel Prize for something they weren't intentionally looking for.
Surprise, here's your Nobel Prize. Yeah.
Exactly. And in realizing this caused everyone to look at their data and go, huh, okay. And as people started going through all their data, we were able to get things to more or less make sense, looking at the WMAP data, later looking at the Planck data to measure the acceleration of the universe based on the cosmic microwave background. We had multiple teams using supernovae, using gravitational lenses, using a whole myriad of observational properties in the more recent times in the universe. And for a while, the error bars on all of these results were sufficient that they overlapped with the error bars. But as the error bars have gotten better, they don't overlap anymore. And so we have a universe that appears to be accelerating apart with a discontinuity, or we don't understand the physics that goes into interpreting our results, or there's just something else going on out there.
Right. And so again, I mean, our job is not to explain what these things are. Nobody can. That would get us a Nobel Prize if we could successfully explain it. But what are the big pillars? Again, if you want to overturn this idea of dark energy, what observations does your theory have to explain?
You have to be able to explain the change in brightness or change in velocity of type 1a supernovae over the age of the universe. So either you're explaining that the supernova actually had different brightnesses over time, or you're explaining how the acceleration of the universe changed over time. Both things fit the data, which is a headache.
Yeah.
You are also explaining the distribution in cold and hot spots in the cosmic microwave background radiation and the other wiggly niggly differences that we find in that tiny splattering of variation that represents the universe roughly 400,000 years after it formed.
Right.
And you're hopefully explaining why observations of the modern universe, including with gravitational lenses measuring the physical distances to galaxies that are changing in brightness in interesting ways, all seem to give one set of numbers. And observations of the cosmic microwave background give a slightly different set of numbers.
I think that is sort of to a person's advantage that if you are trying to overturn cosmology, because, this is the crisis in cosmology.
Yeah.
This is so.
That's what they call it, is the crisis in cosmology.
So if anything, this is a point where astronomers are now actually very aware that there is a discrepancy between the velocity measurements early on in the universe and the ones later on in the universe, and above and beyond what's predicted by dark energy. And
what's going to be fascinating in watching theorists try and deal with this, the observers are out there beating on their error measurements, replicating what they're doing.
Yeah.
The observers, they're having a good time with this one while making their technology work at the edge of its bestness. The theorists, on the other hand, are out there writing papers that have no more than 2 authors with potential explanations. And this is what we're going to see, is papers with no more than 2 authors, because that's how many people can get the Nobel Prize. And there was an interesting one that came out this week that we discussed in the Daily Space on how maybe there was a phase transition in dark energy.
Yeah, I saw that.
Where it changed from one state to another, and that with it changed the evolution of our universe. And I've seen stuff like this pop up before, where people point out, well, there was this age of inflation in the first few minutes of the universe where crazy stuff happened and then it stopped. What if there was yet another change over time? And so those are intriguing, but they're not definitive. And so we need something that is able to explain all of this and convince all of us that it explains all of it.
Well, and I think that's a good place to wrap this. So if you have a theory of everything, if you think that you have figured out why Einstein was wrong, it's more than just Einstein. And I think the first best step I think that anyone should take is to fully educate themselves at the state of the science as it stands today. Be able to replicate the mathematics that the people who you would like to be peer reviewing your paper are going to be doing if they actually are willing to peer review your paper. And to not do that is, I think, a sign of, I don't know, like almost disrespect to the amount of work that's gone into the discoveries that have been made so far. And people have not just made this up.
Never write to somebody and say, I have this idea, but I'm unable to do the maths.
Yeah.
Can you do the maths to prove my idea for me?
Yeah.
I don't even like to do my own math, people.
Right.
Don't ask me to do yours.
Yeah. It's like coming up with an idea for a novel and talking to an author. All right. Thank you so much, Pamela.
Bye-bye.
Now, do you have some names for us?
I do. I just need to move things around on my screen. So as always, we're brought to you by you. Your contributions on Patreon, your donations. You are what allow us to keep bringing you content week after week, year after year. And this week, I'd like to thank some of our Patreon community members. Specifically, I'd like to thank Anthony Burgess, Donald Mundus, Andrew Stevenson, Antisaur, Scott Bieber, Jen Grunwald, Rachel Fry, Bart Flaherty, Kenneth Ryan, Sean Freeman, Bixa the Cat, The Air Major, Samansky, Dean, Tim Mackin, Glenn McDavid, Benjamin Davies, Nalia, Kansenia Pimplinko, Shannon Humber, Kimberly Rack, Gabriel Galfin, Froda Tenenbaugh, Niall Bruce, Daniel Loosely, Alex Rain, Corinne Dimtrick, Neuter Dude, David Gates, Justin Proctor, Abraham Cottrell, Joe Wilkinson, Claudia Mastriani, Jean-Francois Rejot, and Iran Segev. Thank you so much, all of you, for being here for us and allowing us to do what we do.
Thanks, everybody. And we'll see you all next week.
Bye-bye. And now be safe. So for those of you watching over on YouTube, I just want to say we're going to be recording this week's Daily Space right after Astronomy Cast over on Twitch. So if you want to join us after the show, after Astronomy Cast over on twitch.tv/CosmoQuestX, you can get even more science. It's mostly Earth science today.
That's what I was going to ask
Earth's
you.
a planet.
I'm intrigued. What's the topic?
So we're a news roundup. So we're doing a rundown of some of the basic things that have been found, some Hubble observations of another star dimming like Betelgeuse. And then there's a whole lot of Earth science going on. I'm going to talk about one of my favorite things, which is what volcanoes can do. And in this case, it includes
destroy everything. Hopes, Pamela.
well, yes, but preserve things as well. Pyroclastic flows don't just give us human history like Pompeii and Herculaneum,
Sure.
but there's a forest that was preserved on Lesbos. So we're going to talk about that and what it takes to preserve things that maybe someday we can use to look for things on other worlds.
Very cool. How would you like to answer some questions?
Let's do it.
Okay. Corey S. asks, how do we account for dark matter not giving the appearance of affecting orbits at the solar system level?
It's just not dense enough at the solar system level. One of the things that brought home to me the density of dark matter is it would take one Acme brick worth of material, like generic bricks, like the ones behind me in this wall. Take one of these generic bricks, stick it in a solar system sized volume of space.
Right.
And that's the density of dark matter.
I'd heard it was like a small asteroid, not a brick, but still a teeny tiny amount of dark matter would meet your needs. And so it's just not going to affect it gravitationally. The solar system is special because it's concentrated matter.
Yeah.
But for every concentrated solar system stuff, there's vast areas out there that are totally empty. So,
Except of dark matter.
The dark matter is an average across it. So
Right.
Hal McKinney asks, how could the gazillions of neutrinos out there not be constantly bumping into each other? If they bump at all, like traffic in Houston, wouldn't neutrino traffic start backing up and get cold?
It's a matter of the size versus the volume. If you let loose 10 kittens in Terminal D of DFW, Dallas Fort Worth Airport,
Yeah.
those 10 kittens aren't going to find each other. If you instead let loose 10, I'm trying to figure out what wouldn't destroy everything. Let's just say something that would destroy everything. You instead let loose 10 tank engines.
Right.
They're going to find each other.
Right.
And so because neutrinos are so remarkably tiny, they're not going to collide together. Release 10,000 BBs down the back of a theater.
Right.
Most of them won't hit chairs. It's just a matter of density.
Right. So the cross section of neutrinos is very small. They just don't bump into each other. They don't interact with you, and you're made of stuff, and they don't interact with each other.
It's true.
Yeah.
And 10,000 in a theater is probably an exaggeration. Release 100 BBs in the back of a theater. Most of them won't hit a chair.
Right. Trey Harmon asks, central to the discussion for me is how do we know how much stars and how much normal mass resides in each galaxy? How do we know?
So we literally measure how much light there is. We make assumptions about how much mass is tied to that light when we're looking at something far away. And then we look at what are the rotation curves of that galaxy. It's called the mass to light ratio. Measure how much light, measure how much mass, look at the ratio between the two. And we find very different mass to light ratios on different kinds of systems. Like globular clusters don't really have dark matter. Dwarf galaxies quite often have stupidly large amounts of dark matter.
Right.
Which is how we know that even though these two things have similar numbers of stars, they have very different formation mechanisms.
And I mean, don't we know the mass of an object by measuring its orbit around another object?
That is the best way to do it, yes.
Right.
But that requires a binary system.
Right. Two galaxies orbiting around each other.
Yes.
Or a galaxy is part of a galaxy cluster.
And with an individual lone galaxy, you look at, assuming it's edge on, how fast one side is coming towards you and the other is going away from you. And this rotation curve gets you at the ability to do calculus and figure out the mass.
Right. Paul Disney asks, what is a theater? Oh,
What?
is a theater.
I understand.
Yeah.
I don't know about you, but like for the most part, I'm irritated at being trapped in my house, but I hadn't really had, other than traveling to see humans that I like, any real I miss X until last night when I had this terrible desire that I still have now for a chocolate cake glazed donut from Dunkin' Donuts. Like I just miss the smell of going into a Dunkin' Donuts
That
and
feels
getting
like a thing a person could still acquire. Food mates or
except
something.
we don't have them locally, and I always
Oh,
got
okay.
them when I flew home to the Boston area. And since there's no flying to my childhood home,
Right. Yes.
yeah, I
I'm
miss
sure we could find you Dunkin'
Donuts.
Donuts. It's kind of close to where you are. I'll just
They're,
let
the
me just Google
nearest is
that.
about 30 miles away.
Perfect. And then now you can't like go in, and you
Right.
don't want to send Kyle in, but you could probably call them from outside and then figure out some kind of transaction where they can come in.
They have drive-throughs. It's just,
They've got drive-throughs. Okay.
yeah.
This just yeah. So a buddy of mine was coming through town, and he was like, "Oh, we should get together for a beer." And we've got a great little microbrew place here, and I would love to sit down and have a beer with him. But COVID outbreak, no way. I'm not going
Yeah.
anywhere near the brew pub. So
Yeah.
I'm like, we could go for a walk instead outside.
Our local brew pub delivers. So I have
Yeah.
gotten beers delivered.
Hal McKinney is really troubled. Why aren't neutrinos more dense than you're giving them credit for? Where are they all going? Are we getting bombarded with neutrinos from all suns everywhere, not just our own?
Yeah,
Yes.
that's
They
a
have a
thing.
very small cross section.
They're just tiny. It's
Yeah.
sort of like you don't notice the air in the room you're in.
Well, what was
There.
this idea that if you took all the matter of like planet Earth or something like that and compacted it down to the actual size of the atoms, it would be the size of a sugar cube. This is like a Neil deGrasse Tyson
It's
thing.
bigger than that. But yeah.
There's like like if you, like you're sitting on the chair, but it's not like the atoms on your body are touching the atoms on the chair. They're actually hugely separated.
All electrostatic
Right.
electrostatic forces
Right.
preventing me from falling through the chair.
Yeah.
Because there's plenty of empty space in my body to fall through this chair.
Yeah. It would be a
And-
piece of cake if you didn't have that force.
Yeah, the electrostatic force is our enemy. It's also our friend because admittedly falling through the chair
Yeah.
would kind of suck. I like this
Yeah,
chair.
there would be problems. You'd also fall through the ground. So it's just like and this is the term, the cross section.
Yeah.
The cross section of the particles is very small, incredibly small, so small that they don't bounce into each other very often. And I think that, so small that there's like Ice Cube, which is a cubic kilometer of ice, and they detect a couple of particle events a day. I don't even know how often they detect a neutrino passing through a cubic kilometer of ice and
And
interacting.
it's detecting the high energy, the 200 tera electron volt and higher energy neutrinos that are coming to us from shredded stars and blazars.
Yeah. So it's just the size of the particle, or the cross section
Yeah.
of the particle. Because
And
size
we're
is
also oblivious to the cosmic microwave background, which is going through us all the time. We're oblivious to
the
light in general.
but isn't-
There's
wait a
so
second.
many particles that we just don't notice.
I mean, the cosmic background isn't going through us,
no, it's hitting us.
hitting
That's
us.
true.
Yeah. But cosmic radiation is passing through
Yeah.
us and
Yeah.
tearing out our DNA.
Occasionally, yes.
Yeah. So that's it. And so he's like, how do you know? So
I
the math that predicted the neutrino defines the cross-section, defines many of the characteristics of the neutrino, defines that if it does interact with regular matter, what is the outpouring of particles that will happen. And those were all observed.
and that's the key thing is there were initially, as there are for so many different things in astronomy, a myriad of different theories. And even when I was in graduate school, there were massive arguments over whether or not neutrinos had mass at all.
Mm-hmm.
And for a long time, there was this huge problem of understanding the solar neutrino problem because we just weren't seeing enough neutrinos coming to the Earth in the right type to explain the fact that our sun has nuclear reactions, because those nuclear reactions predict certain numbers of neutrinos in certain types are going to be formed.
Right.
And it was finally realized that neutrinos have this amazing capacity to rearrange their mass and energy so that the mass energy is conserved. But as they're going along, they'll convert between different flavors of neutrino and keep that mass energy total constant.
That was surprising.
It was amazing.
Yeah.
And neutrinos are weird.
And
awesome.
And that is a fairly new, I mean, we learned that neutrinos change flavor just a few years ago.
Yeah.
Shambro asks, what other theories or merit are around that challenge the concept of dark energy? I think that's fair. Like dark matter is pretty rock solid. Dark energy, it could be explained away.
Dark energy, people have tried to explain it as vacuum fluctuations of particles, but that is off by 140 orders of magnitude last time I looked. So clearly, vacuum particles don't really explain it. Like I said, there is a cool paper looking at it as a phase transition. Various people have looked at it as being related to the same factor that caused the epoch of inflation. Mm-hmm. Nothing has really captivated the entire community enough that we were willing to jump on and go, yes, let's explore this more.
I mean, the one that's fairly recent is this idea that the matter that went into the supernova, the Type 1a supernovae, was different. The recipe for Type 1a supernovae was different earlier in the universe than it is today, just because the elements or the amount of metals that would have gone into the star were different, an early one versus a more recent one. And so it might actually be that they're not the same brightness, that they're differing brightnesses based on the age of the universe. And that would nicely explain it.
And that has been what people have been hoping to prove ever since 1998.
Yeah.
Where we run into issues is we keep finding fully formed galaxies early in the universe. Yeah. And if you can have a fully formed galaxy 600 million years after the Big Bang, it's going to have churned up a whole lot of metals. Yeah. And we're not detecting Type 1a supernova from 300 million years after the universe began. Right. We're detecting them from much more recent times. So there is the ability for metals to have built up, and then it becomes a matter of, well, does the dispersion in brightness that we see change as a function of time? And we're not there yet, which is why we're so looking forward to instruments like WFIRST, which is now the Nancy
Grace Roman.
Thank you. I kept going Rubin, and I knew that was wrong.
That's Vera, yeah.
The Nancy Roman telescope is hopefully going to be finding more data that we can use to constrain our theories.
So Hal McKinney again asks, okay, so how do they measure the density? So it's math. Yeah. How do they measure the density of neutrinos? So you take the total amount of nuclear reactions that are going on in the sun, 4 million tons per second.
I love the random numbers that you store in your head. I do not do this, and it is impressive.
1.5 million tons of stellar materials being blown off the surface of the sun, while 4 million is being converted into helium at the core of the sun. So you take that 4 million tons of stellar material, you determine how many neutrinos would be generated by that amount of nuclear fusion, use the inverse square law to measure the number of neutrinos that will be leaving the sun at every point of distance. And at the point that we are away from the sun, you have countless numbers of neutrinos passing through your body. I'm sure there's some number specifically.
There is.
yeah.
I remember learning the number that should be passing through your pinky fingernail.
Yeah.
I do not, because I am not you, remember what that number was.
Let me just I'll pull up the number. 100 trillion neutrinos are passing through your body. Most come from the sun.
And the way we were able to confirm this isn't hogwash, other than the fact that the sun works, is once we were able to start detecting neutrinos here on Earth, we know how often they should interact, and then we could measure how many we could see. And if you know how many react for every 10,000, for every 100,000, you count up the number that react,
right, and
you multiply it to get at what is the total population of neutrinos. And it's kind of cool. It's just math.
Yeah, I mean, I think the key was finding one of them.
Yeah.
Right? Like that was the hard part, was that if the theory goes, like the story of the neutrino is really interesting, but at some point someone just did the math and said, if this is how the sun works, turning hydrogen into helium, and this is the process that's going on, then it should be producing this particle called the neutrino. It
needed something to conserve the properties, so that everything there's a bunch of quantum properties. You have to conserve them. This requires neutrinos.
But it's like every time you do the transaction, you get a little change.
Yeah.
And that change, like if it's money, you turn 4 hydrogen atoms into 1 helium atom with like a little, or 2 helium atoms, I forget the number. Anyway, with a little change left over. And we know there's gamma radiation as part of it, but there was still a little left over. And so somebody proposed that there was this additional particle. And then they spent 30 years trying to find it. And it wasn't until they just created larger and larger volumes of water that they finally found these particle interactions. It's an amazing story. And the ice cube is, I mean, I think Ice Cube doesn't get enough credit as one of the mega telescopes on Earth.
Yeah, because it's a different kind of scope and it confuses most people.
Yeah. And in fact, they're building they're working on the next version that's going to cover 10 cubic kilometers of ice, which is just mind-bending.
That's amazing.
And the hope is that they'll actually be able to detect, like, we talked about this a couple of weeks ago, the background neutrinos of the universe. The ones not formed in the sun, which you're really close to, but the ones that were formed during the Big Bang, which you're very far away from.
And what gets me is some of the cool experiments they've done. Like at one point, they were creating neutrinos in Italy and shooting them, they hoped, in the direction of CERN to detect what number of them changed identities between Italy and CERN.
Amazing.
Yeah,
also,
they do cool stuff.
Accidentally discovering that they move faster than the speed of light, which they don't.
No, that was a loose connector.
Yeah.
Always check your connectors, people.
Yeah. All right. Janelle Duncan asks, Crispy Fried Man on Twitch asks, is dark energy even energy?
We don't know. It's a really bad name.
Yeah.
Really bad. Really bad. It could be a pressure. It could be a force. It could be an energy. We don't know.
But it behaves like, again, the description you always have used is that it's as if there is this outward pressure in every cubic meter of space in the entire universe that's constantly pushing outward.
Yeah, it's like a scalar field of some sort.
Right.
And this is where people jump to like resurrecting the idea of quiescence and the ether and all those kinds of ideas.
Yeah. I think we are reaching the end. So
okay. So as a reminder, if you're already on Twitch, stay there. Stay.
Just stay on Twitch.
Good humans.
And if you're not, go to Twitch.
Twitch.tv/CosmoQuestX. And I'm going to do some pre-show prattling while I set up, and as soon as Beth gets out of a meeting that she's in, we're going to be recording today's Daily Space. There is going to be a game played by Gordon, who's been doing the simulcast for a few minutes, however, because I have to like swing monitors around and physical things like that before I can take over.
All right, sounds good. Well, thank you everybody for joining us. Thanks to all of the mods. Thanks everyone watching on YouTube and on Twitch. We appreciate all of you. But don't go anywhere on Twitch because there's going to be more show in a moment. And if those of you are watching on YouTube, go join on the Twitch side. Yeah. You can continue the party. All right. Thanks, everyone. Thanks, Pamela. And we'll see all of you next week.
Bye, everyone.